Good morning, and thank you for attending Blue Water's webinar, Eco-Friendly and Economic Solutions for the Energy Sector. My name is CJ Strain. I'm the Chief Technology Officer for Blue Water, and I'm a professional chemical engineer. I'm very focused on techniques for process water treatment and process development in this industry. If you are a repeat attendee of this webinar series, I thank you for your continued interest, and I look forward to our Q&A at the end of the webinar. For those who have not attended previous webinars, my format is very simple. We will start with an introduction to the challenges, and then we'll transition to process technologies that meet some of the challenges that we highlight. Then we'll wrap with Q&A at the end of the webinar. If you wish to receive certificates for PDHs, there will be a contact email address on the screen at the end of the presentation. For groups, I need the meeting organizer to compile a list of attendees with their states of license, and I can only give certificates to those who are active and attentive throughout the webinar, and that attentiveness is tracked through the GoToMeeting interface. So just a couple of notes on PDHs. Let's hop in, shall we? I would like to begin by highlighting some of the challenges encountered by many of our customers within the energy sector. Those challenges include and encompass reduction of residual elements deemed by regulatory agencies as being harmful to the environment. Those elements can be in a variety of oxidation states and chemical forms, but include metals, metalloids, and nonmetals. Quite often we're seeing extremely low limits, especially in the energy sector. It represents a big challenge because often in cooling towers, in different applications like coal plants, FGD plants, there's a very high level of dissolved solids, often contaminated with these metals and metalloids that are of concern to the environmental regulators. And the limits that we have to achieve are anywhere from 5 to 10 micrograms per liter on the low end, up to 0.1 milligrams per liter on the high end. But quite often these can be a significant challenge to a lot of folks within this sector. There's also the problem of mercury in a lot of these applications, especially energy generation stations that use coal or any kind of pretty much any fuel. You can get trace contamination with mercury. And that's been, a key highlight with a lot of the regulatory acts that have gone through. The Great Lakes Initiative pushes mercury discharge proposed limits down to 1.3 nanograms per liter. And that can be a significant challenge, one that Blue Water has a lot of history with, which I will share. But quite often we're faced with the decision either to find a way to comply or to discontinue operations. There's always a lot of political stuff going on in the background with that decision, but basically with compliance, continued operations is a straightforward decision in something that we all obviously want. So I'm going to talk about some new designs, new process designs, new equipment designs, and retrofits that Blue Water has provided to the industry to continue these operations to reduce the regulatory costs of compliance, etc. On the screen here, you see a map and a table of different elements, metals, etc. Here's a more detailed look at example constituents that the U.S. EPA is targeting in current regulations and future recommendations. The rest of the world and our experience is really tightening up as well. Anyone familiar with permitting a mine, for example, or an energy site or other industrial sites knows that the list of constituents is usually many times longer than this list here. Now, this other picture here is just a picture of the United States with colored coding for various states, and this has to do with their level of compliance regarding nutrients, total phosphorus, total nitrogen, etc. Not usually as big of a concern in this industry, but it can be a concern across the board because there are many states that are complying with the Clean Water Act. in regard to setting nutrient standards, in regard to setting specific discharge standards for metals compliance. A lot of the resources for where a particular state is can be found on the website, the EPA website online. And this is just one example of an interactive map where you can click on a state. It'll give state information, quite often even county information, on discharge requirements for nutrients. And then it's also a good resource for learning where metals requirements are for a given region. Most of our clients in the past have come to us with a permit saying, hey, we need to meet this. If you're doing industry research and cost analyses, et cetera, and you don't have a specific instance in mind, this is a good place, a good resource to get regulatory requirements for a given location. So again, just a broad overview of of what the requirements are within the industries, and that can lead to an understanding and a description of the discharge challenges, the treatment challenges. So what I want to do is to share some of our success in addressing these metals to the levels of concern. I'm very confident that there are economic solutions, and that the solutions that I'm going to be sharing are much less expensive than what folks are maybe even already doing for previous levels of compliance. Before I really jump into the nuts and bolts of process treatment, I want to provide a summary overview of Blue Water, just share our story a little bit. Blue Water's story is really homegrown in the USA. We're a company that grew up out of a couple of older companies. We have a filtration side that has been around for 30 years. Blue Water as an entity has been around for 10 years, servicing the industry, not only the energy sector and industrial discharges, but also the municipal industry as well. We really produce process equipment for a variety of applications and across the board. We focus on being a solution provider as well as being a unit process, high efficiency provider as well. A lot of our product development is in increasing efficiency of unit processes. We provide turnkey solutions, mobile solutions. You can see a lot of our equipment, pictured on this slide here, even our mobile equipment, where we'll put a complete package plant on a 50-foot trailer. And we'll use these for pilot treatment or for small-scale treatment. And we can also scale this up to much larger skid-mounted systems for a lot of our industrial clients as well. We have a UL-listed panel shop, which really helps us to integrate into existing plant SCADA systems and really customize to the customer's needs as well. So those are a few highlights of Blue Water's capabilities. Again, a U.S.-based manufacturing company, so we're local. We have a very strong operations presence throughout the U.S. and great support group as well. Part of our operations really revolves around modeling the process on the front end of the project. I may have mentioned bench testing before, and it's often the first step in our process development in many of our projects. I have access to a state-of-the-art lab through my operations team, and I use it to model new applications in a very thrifty fashion. Every process water is slightly different, and we can identify many of those process variations in chemistry project to project before the client invests a significant amount of resources. For example, this picture here is a coal, an FGD plant application, where we were interested in removing mercury, selenium, arsenic, and a couple of other trace elements as well. And you can see this is one water sample. It's just been split into two jars. You can see that in removing or targeting those elements, we can, in many applications, we also get a fair amount of precipitation of other dissolved solids. And so that has to be managed through the project and through the process design as well. So again, a very inexpensive bench scale can highlight some of those design considerations and some of the treatability capabilities of our unit processes. We have a variety of other equipment pictured here, a couple of shots from our analytical lab where we're analyzing water samples as well. So again, this is a very thrifty, very cost-conscious way upfront of defining a process. Usually the next step after a bench scale is to pilot, to demonstrate the process in line, a continuous flow treatment system. So pilot testing is sometimes needed following bench testing to obtain scale operating parameters, chemical usage, and energy requirements as well. A bench scale makes a life cycle cost estimate possible, but piloting can really add the precision needed for an economic analysis and get much closer to the real mark to get into a project. So Blue Water has a very capable pilot fleet. We pilot a variety of different unit processes from our product lines. You see a couple here. This is a DAF system that we'll bring around to a lot of industrial sites. This is an Eco-mat rotating belt filter. It's an ultrafine screen for capture of total suspended solids, typically more in the fibrous solids, agricultural, food processing, municipal markets as well. What we're going to be talking about today is really going to hinge on this family of equipment. This is our Centraflow filtration brand, and within it we use our Blue Pro adsorptive process for removal of metals and nutrients. We can also do biological treatment within those vessels as well. There's a variety of different reasons to perform a pilot that we've hit on a couple of them, but we can use these pilot systems for treatability projects and studies, for research, as well as for pilot scale for design, as I mentioned before, to really feed economic analyses and get projects off the ground and going. Also to instill engineering or provide engineers with confidence around the process, and really give them the tools they need to develop a comprehensive project plan and get approval for that and execute. We also provide these systems for contract treatment as well, anywhere from a few gallons per minute up to a few MGD, depending on the application. So those are a few different opportunities that we service with our pilot fleet. Let's get into the process of removing trace metals, because that's really what I want to focus on today. Here are some examples of projects currently in design and construction phase. We have a project right now that's being commissioned in Minnesota. It's actually got a really neat story. This is a municipal project, but this site has been permitted with a very low mercury discharge level. I highlighted on the Great Lakes Initiative earlier on with very low 1.3 nanograms per liter mercury requirements. This is one of those projects. So we've installed, we piloted early on in the project design phase, got the design parameters for the engineer, very well put together package, and now it's being commissioned. It's been, Blue Water has worked through that entire project life cycle. We have a municipal plant, the design also that's going into Montana. Very similar application, but it's in a location that's a mining district. So they had smelters going on. There's a lot of copper contamination, a lot of lead contamination, and zinc, and they have a minor nutrient consideration as well. So this was also piloted earlier on. So again, highlighting the use of our pilot systems, and it's now in completely been designed. It's bid already. It's in construction. So we'll be commissioning early part of next year. We have another project in New England. It's an industrial project. It's actually a landfill, but the reason I bring it up in regard to the energy sector is it has a lot of the similar contaminations and considerations that we're chasing after. We're looking at arsenic removal and selenium removal in that application. We started that one with a bench scale and are proceeding with a pilot with that particular project. So I would say that's kind of midlife right there in design. This is another one that we've done recently. This is an industrial process in Iowa. This is an energy facility. They have holding ponds where they basically will discharge from. They have tightening aluminum and zinc requirements. Not extremely low. We've seen much lower, but again, these are their requirements at this particular site. We've seen them, range all over the board. We've already done bench testing and pilot testing that were very successful, so we're moving into the design a design phase with this particular project. So just a highlight of some of the different projects that we face, some of the different elements that we're addressing, and again, the level of each of these elements will differ from project to project. You can see some of our equipment and installations pictured in this photo. Here's actually an apparatus that we use for a bench scale test. It's a flow-through system, typically a batch process. In the lower left picture here, you see one of our mobile pilot systems. It'll treat anywhere up to about 70 gallons per minute as a peak flow if those filters are run in parallel. And we can also configure those to run in series if we need to. And you can see several of our installation photos here for these filters, the lower part of this slide. In most applications, we're looking at a very basic process flow for treatment, possibly needing a clarification system up front followed by an absorptive filter for metals polishing. And that metals polishing is really what we focus on as our key advantage within this industry. I skipped through this one. So as I mentioned, a lot of our projects we're just chasing after compliance for trace elements. But a lot of times when you trace it, when you're targeting a specific element, say like zinc, zinc is an element that likes a higher pH for absorption. You'll get some precipitation of dissolved solids if you're in an application that has very high TDS. So it's often necessary to have a clarification, a precipitation stage up front, followed by our Blue Pro system. And again, this is really the key for compliance throughout our conversations and process design. So I'm going to be spending a lot of time defining that unit process as we go on here. Some of the design considerations that we use within our product development and implementation are, highlighted within this stage or this page here. Treatment quality is obviously the topmost concern. We have to be able to meet the quality requirements that are laid out for discharge. And then secondly, we want a simple system, something that operators do not have to spend a lot of time overseeing and interacting with on a day-to-day basis. We want something very simple. And as you'll see throughout this presentation, the technology that we have developed is a very simple system. The vessels that we use for treatments, they've been used in the industry for 10 to 20 years. Our processes have been developed within the last 10 years, but again, they're very simple and straightforward from a control standpoint and from an operator interface standpoint as well. And what these another design consideration is often a multi-barrier approach. Maybe not in every application, but in some applications they cannot, violate permit at all, and so they have a redundancy consideration. A lot of people can get around that by having additional impoundment or holding capacity on site, where if they have to do some system maintenance, they can store the water and then treat at a higher rate as they come back online. So, what the site requirement is in regard to that, treating water during maintenance activities or during washouts or something like that, whatever the case may be, is definitely a consideration throughout the process. Ease of maintenance goes right along with simplicity. We want something that's very efficient, low cost to operate, low chemical input, low energy input as well. And then safety, of course, is always a consideration, right along with the environmental odor control issues, etc. The bottom line for all of these considerations is capital and life cycle costs. We focus really on minimizing those to the utmost. So I mentioned quite often in our treatment train, if we're targeting a specific metal like mercury or any of the transition metals that require a higher pH, you can quite often get some precipitation of dissolved solids. So a lot of times when we're putting these systems together, we have a clarification stage up front if the site doesn't already have one. And that clarification stage will typically begin with a flash mixing stage, which you see in this process flow going from the right to the left. A flash mixing stage where you're doing your chemical injection, your pH adjustments, any flocculant addition. You're doing a maturation process to form that large particle size that will easily settle and separate out from the processed water. And that enters a high rate clarifier. Typically, we'll use a high rate incline plate clarifier, something like a lamella type. Our product line is the Eco-55 IPS, and these are very high efficiency clarifiers. They minimize footprint and a lot of the operating costs, and they have very simple, straightforward access to sludge management, etc. So a lot of times this is necessary, again, in situations where there's a high TDS. We model all of our systems in 3D CAD, so it's very simple for us to do layout and arrangement drawings through a facility plan, and we do all of our construction within the U.S. for our incline plate IPS line. Now I'm really going to focus on what sets blue water apart from other treatment technologies out there, and that's really the efficiencies that we can gain by integrating an adsorptive process into our treatment flow. So we use the Blue Pro process after that precipitation or clarification stage to adsorb to extremely low levels all of these metals of concern. We can get even higher removal rates with two-stage systems and our recycle of our process reject, which has some residual reactive chemistry to it. Another application for a two-stage system would be where you're targeting two different types of metals, where maybe in the first stage you're having to raise the pH to target transition metals like zinc, like cadmium or copper, lead even. And then you're going to another stage that might be lower pH to target elements like arsenic and selenium, some of the nonmetals and metalloids. Also phosphorus, it likes a larger band, or has a larger adsorption band than a lot of other elements, anywhere from 4 to 10 it will absorb, but it's strongest just below neutral. So those are also applications where you might need a two-stage system. But one thing that I like to highlight is that blue water can do all of its process design in CAD. Again, we do all of our process designing in 3D CAD, so it's very simple to do a facility plan, site layout, etc. I want to highlight that some of the applications that we've really targeted with Blue Pro adsorption for meeting these trace residual metals requirements, and give some very basic rules of thumb for application. Nearly all transition metals can be treated, so that's basically anything in the center of the periodic table, anything in this blue. So I mentioned zinc, I mentioned cadmium, and copper before. Also mercury falls within this zone as well. So these can all be absorbed very easily, slightly higher pH, but they'll all absorb. The metalloids and the nonmetals, quite often their pH adsorption isotherms are a little bit different. They can be neutral, they can be high, they can be low. So it really depends on the element, and this is really where our process history comes into play with new applications in process design. We have excellent case history for phosphorus, arsenic, selenium removal systems. There are a couple of things to stay away from. There's no treatment of light molecular weight alkaline and alkaline earth metals. So sodium, lithium, magnesium, not going to be a great application for the Blue Pro adsorptive system. You might be able to get some of that out with precipitation stages up front, but again, it's not going to lend to treatment efficiency within the Blue Pro system. And there's limited treatment of halogens, which would be on the right side of the periodic table, your chlorides, your fluorides, your bromides, etc. Very limited removal rates for that. The fluoride is actually the best, but you're probably only talking about a 10 to 20% efficiency at most. So again, stay away from the halogens. If you're looking to apply the Blue Pro process, it's more in the middle of the periodic table where it has its highest efficiencies and strengths. I want to highlight some of the benefits of this process. Again, Blue Water does all of our design in 3D CAD, which is a huge benefit to the project plant layout, etc., the design phase. This is one project we have in Lincoln, Arkansas, where all of the filters are above ground. We have, obviously they're installed outdoors. We have a lot of systems that are below ground systems. You saw a few models of those before. There's a couple of pictures here in this banner at the top of the screen. But what this system uses, what the Blue Pro process uses, are gravity sand filters. And they backwash continuously, so they're a lot different. They're not your grandfather's filters. They're a lot different than the high-rate static bed backwash filters that have been used in the past. Now, these continuous backwash filters, they've been around for 10 to 20 years, and you'll see them or some version of them in a lot of industries. Our product has really been developed to enhance the efficiency of absorption. The nice thing about this platform, these filter systems, is there's no moving parts. So the life cycle analysis for these filters is very impressive. There's no moving parts, there's no wear parts. So most of the components have a 10 to 20 year life. The vessels, certainly the internal assemblies, all 20-year lives. The thing to wear out the quickest is actually an internal airlift, which we give about a 10-year life. It's made out of PVC, and it's like a 5-minute change out here. But the nice thing about this entire system is, in addition to absorbing metals, it gives you filtration to reuse quality and reuse standards. In fact, these systems are California Title 22 approved, and they're approved for reuse throughout much of the U.S., throughout many states. It's a very simple design system. You have a couple of arrows in this 3D cutout here on the screen, so I'll just talk through the process. The water to be treated enters through where this arrow number 1 is entering the filter vessel. It enters through a pipe network or a central assembly that brings the water to the bottom of the vessel, and the water flows upward, as these arrows illustrate, to overflow a fixed effluent weir at the top of the vessel. Now, through this portion of the vessel, there's a media bed. We use a sand-based media which we coat for an absorptive uptake of metals. So again, water moves upward and overflows a fixed effluent weir. There's a wash box that sits within the center portion of the vessel. This wash box is for recirculating and cleaning the media and for scrubbing the spent absorptive coating off the media. So again, this happens continuously, where the airlift will actually lift the spent media from the bottom of the vessel where it's dirtiest, carry it to the top of the vessel, discharge to the wash box, where it'll fall through a baffle. And through the scrubbing action that you get with that airlift, you get a very high energy scrub that'll completely strip an old coating of what we use to absorb these metals, and that'll remove it from the process, putting clean media back to the top of the bed. So you get a countercurrent flow with the media flowing downward, water flowing upward. And what's the water used for the backwash is actually internal to this vessel. So again, limited moving parts. There's just a portion of the clean water that flows up through the bottom portion of, you can think of this as a cylinder, countercurrent to the media as it's falling, so that'll carry away the contaminants out of a backwash stream. So that's how the physical system works. I'm going to talk about how the chemistry works now. What we do is we inject a ferric-based chemistry, and it can be really any ferric salt. But what we're looking to do is, this is a scanning electron microscope image of just a sand granule, one of our medias. These are typically about a 0.9 to a 1.2 millimeter diameter. And again, it's just silica sand. It's a very simple commodity media. What we do is we put a coating of ferric hydroxide on this. So over the entire surface of this media, and this is why we use a scanning electron microscope for this, is we can, under X-ray fluorescence, we can view that coating. So it's got a coating of ferric hydroxide on it, and that coating is very adsorptive to a variety of different constituents that may be in the water. I have phosphorus here. That's what's being analyzed here in this particular SEM slide. But again, we have huge application for a variety of the transition metals, mercury, non-metals like arsenic and selenium, etc. So that's the basis of the technology. All of the chemistry happens at the surface of the media. Now, if you contrast this to what's been done in the past with coagulation followed by filtration kinds of technologies, what they're doing, or what's been done, is you're adding chemistry, you're forming a flocculant or a coagulated particle, and then flocculating it and filtering it. And what that does is you're forming a particle that's too large to fit into the filter or fit through the interstitial spaces of the media. And so what you're doing is you're plugging the filter. And not only is that a reliability issue, but it's not very sustainable. Those systems historically have failed quite a bit. They were always operating on the ragged edge of failure because of the methodology of removal. With adsorption, you're not building any particle size in the water going into this vessel, into this process. You're simply coating the media, and you have free flow of the water across the surface of the media, and that's where your chemical uptake of trace metals happens. So that's a huge difference between an adsorptive-based Blue Pro system and a coagulation followed by filtration process. And our media is really different too. We use a spherical geometry, whereas coagulation filtration systems use a subangular sand, so they have tighter interstitial spaces. And of course, I already mentioned the issue with that is sustainability. They plug a lot. So our Blue Pro system uses, again, a very spherical geometry that can, the media slides against itself very, very well. I mentioned the diameter, the effective diameter that we use for our media, typically about 0.9 to a 1.2. We get a much greater reliability process-wise over conventional treatment techniques. And again, our very high surface area within the bed gives us that adsorptive contact, that chemical contact that we need for the high efficiency. And because of that, we can use actually a lot less media than conventional media filters like the static bed filters, etc. We use significantly less media for the process. Another highlight that I wanted to bring before you is that of the chemical side of this process. The Blue Pro system does use a ferric-based chemistry. It's much better than other chemicals that are available on the market. We can use alum. We have used alum in the past, but there's a lot of aluminum limits out there that would prohibit the use of alum. Alum doesn't attach to media the same way that ferric does, so you don't get that coating on the media with alum. So there's several reasons, many reasons in fact, why we use a ferric-based chemistry. And it all boils down to efficiency. We can also achieve lower ferric residuals coming out of the process. We get a very high attachment rate to our media, and then a very high uptake of trace metals. So again, as I mentioned before, we use less chemical volume, higher efficiencies, and we get better sludge management, more compact sludge with the ferric-based chemistry. Here's a design comparison just between a ferric-based or aluminum-based chemistry using a coagulation filtration technology versus an adsorptive technology. And the usage rates as far as dry chemical are hugely different, as well as the sludge generated and the alkalinity consumed throughout the process as well, pH variations, etc. So ferric-based chemistry is a key to the Blue Pro process. Now, when we're doing a lot of these metals removal applications, we're having to adjust pH again to target specific adsorption isotherms, as I mentioned previously. And that can sometimes be a good recipe for scaling within the media bed. That's what we saw in the industry, many decades past, or throughout the past few decades, with static media filters, where there's no process control to inhibit scaling, etc. So Blue Water actually came up with a process for scale removal and to inhibit scaling that fits within the vessel. That's a continuous process, does not require any additional interaction or oversight from the operator. This can replace outdated airlift equipment and designs, and we've actually retrofitted a lot of older upflow sand filters throughout the industry with this technology. And basically it's just a reconditioning system for media. It can also be used in a maintenance schedule through our PLC to prevent scaling as well. So this can be done with a pH adjustment chemical for media cleaning. It can also be done with anti-scalants, etc. But it's configured to prevent, again, the scaling of media, scaling of pipework and vessels, etc. And it'll really enhance the filtration and absorption efficiency of the process. This technology is patent pending. Again, we've used this in a lot of applications. I've got one in Pennsylvania that's a Blue Pro system that's immediately following a incline plate clarifier, where they have a very high pH in the clarifier to drop out all of their TDS, their metals, etc. They operate at a pH between 10 and 11, and then that process water goes into a Blue Pro system for residual polishing of these trace elements. And so in that particular application, they get a lot of benefit from this media reconditioning system to prevent scale in the media bed. Now I'm going to hop right into a lot of our case history, because I think there's a lot that can be learned and witnessed from the data sets of these case histories. Blue Pro, the process has been around for about 10 years. The first full-scale installation was completed in 2005. It was on a municipal plant, but again, it's the same process that I'm talking about today. A Blue Pro process, this was implemented by CH2M Hill, or I should say that they wrote the protocol for site modeling on this project. And it's in Hayden, Idaho. It's a 360,000 gallon per day system, so a relatively medium or smaller size plant, but some very good operation history. And I've been talking about element residuals down to the microgram per liter limits. This particular plant was dealing with phosphorus that was in the 3 to 10 milligrams per liter range, and by the end of the day after installing a two-stage system, they're having residuals for phosphorus, an element that's conventionally very difficult to remove to these residual levels, bouncing around the 10 microgram per liter range, and, basically maintaining an operating line below 0.02. And this chart covers almost a 3-month period or 2-month period. So a very effective plant for removal of a trace element down to extremely low residuals. And it's been operating, again, since 2005, so we're going on 8 years, almost. We're pretty close to a 10-year anniversary on that plant. This is another Blue Pro installation. The target in this application is arsenic removal. And this project is in Florida. It's groundwater cleanup. It's in one of those historical ranching districts where they used to use arsenic baths for control of pests that could, be harmful to the cattle and could be disease-carrying vectors, etc., like ticks, etc. So they would use arsenic baths, arsenic dips all over the place, and it just saturated the ground in this particular region. So this it's on tribal land, so the local Indian tribe was involved. The engineer in the state was involved to really clean up the groundwater, which is anywhere from 1 to 4 milligrams per liter of arsenic. So it's very high arsenic content. That's anywhere, that's 1,000 to 4,000 micrograms per liter. Their target was really to get under 100. So we went in with this small package system. It's in a remote location, so it's a completely self-operated. It's got telemetry in it so that operators can monitor it and control it from afar. And it just slowly turns over the groundwater to remove arsenic. All of the sludge management, all of the chemical systems are all within a container on site, and this system will treat 36,000 gallons per day. Here's another much larger installation that we installed of this technology. The engineer was CDM Smith. It's an installation in Marlborough, Massachusetts. It's on the municipal side, but again, polishing a trace element, phosphorus again, a nutrient, very low residuals. During the performance testing at the front end of this project, we averaged a 0.02 milligrams per liter total phos. So a very capable single-stage system for removal of that element in a very large installation. This illustrates our concrete design, which is typically our below-ground installation design. Here's another another project that's in process for cadmium and copper removal. It's a U.S. energy site in Colorado. So far, we've done the bench testing and the piloting within the design, the life cycle of design for this particular project, and we're now into to design for full scale. The pilot system was a 50,000 gallon per day system. The deliverable was currently, for current needs, are cadmium to less than 0.5 micrograms per liter. Also, they might have much lower requirements in the future, so they were looking at cadmium, copper, and zinc, and also aluminum actually for this particular project. And so those were measured throughout the project just to see where they could get in the future for any tightening, any further restrictions on their site. So cadmium below detection limits, copper to less than 0.8, zinc to less than 3 micrograms per liter. So a very effective process for removal of those trace elements. Blue Pro installation for zinc. This is in a historical mining district, another one of those where there's cadmium and copper contamination. This is a municipal site that got hit with a permit level for phosphorus and zinc. So you see the permit levels here. This one has actually been highlighted a couple of times in local water conferences because it was really the first of its kind to go in. It's a very effective installation that started with a bench scale, went to pilot phase, and then very quickly into installation implementation for the client. Typical performance for the phosphorus is again in dips down to that 10 microgram per liter range. Zinc very typically less than 0.1 milligrams per liter. I'm sorry, and again their target is 0.2. Here's another location that highlights mercury. This is International Falls, Minnesota. Engineer was Widsa Smith Nolting. And this is a larger system. There's 14 models, CF64 filters for a treatment of 3.2 million gallons per day, average daily flow. The design peak was 4.7. Now the deliverable here, they had a phosphorus permit, but that wasn't really the key focus for this project because you can do that level of phosphorus removal in a clarification system. They needed to hit 1.3 nanograms per liter was their target for operations. And so they brought in the Blue Pro system. This was one that started with a pilot system operation back in 2010 and proved it out really well. They were able to push up to a 6 nanogram per liter mercury limit on their discharge permit. And obviously to meet that and maintain it, they're going to have to really essentially get to non-detect, which is below 1 nanogram per liter. Now we're talking nanograms per liter, which is insanely low. There's there's a million nanograms per liter in a milligram, I believe. Yes. So it is an extremely low, that's parts per trillion concentrations in water. So it's, again, just highlights and illustrates the efficiency that can be had with an adsorptive process. In addition to our adsorptive processes for a lot of these industrial sites where we're removing metals, heavy metals, even some of these non-metals we've covered, we can also do biological processes within the same vessels, within the same treatment stage, because we get quite a bit of residence time within these vessels. We can add biological treatment considerations in a lot of these applications to remove things like nitrates. We can get some slight scrubbing of seleniums and sulfates as well with a biological treatment system. But mostly our focus is on the nitrate uptake and removal because it's a very high efficiency process and requires anywhere from 10 to 20 minutes for most of our applications, which is residence time that we can achieve. It's a biological process where you have to feed a carbon source for cellular respiration, and then they get their oxygen requirements, their electron donor is from the nitrates. Alternative carbon source options are available like glycerin, but typically a lot of the industry uses methanol for its high efficiency. Now again, one of our design considerations is process safety and cost minimization. So the glycerin products or the alternative carbon sources are nice because they get away from the explosion-proof design that you would have with methanol, and it's also safer to work with, of course, too. So again, that could be cost reduction, cost mitigation. It just depends on the application. We've done a lot of these applications in the mining industry. Here's one of those. It's in South Dakota. They're running this to remove a very high level of influent nitrates, 150 milligrams per liter. And their target is less than 10. Typically, they're actually operating at non-detect coming out of the system, just again because of its high efficiency. But this project, the first installation was completed in 2011. They've gone through one expansion, I believe, in 2012, and they're going through a second expansion planned for implementation in 2014. So this particular site is a very good case history for removal of not only trace elements, but a biological process for removal of concentrated nitrates. Here's another one of those where we have a dual system. It's a Blue Pro adsorptive system in combination with a Blue Knight system. This is a much larger municipal plant where you're doing both a adsorptive uptake of a phosphorus element and biological removal of nitrogen. So that was, again, started with a pilot. Installation was completed in 2009, and it's been running ever since. So there's another good case history with Nittany Engineering. So again, I've highlighted throughout all of these case histories the efficiency of the process, the different targets that we can achieve, and really, again, I hope that I've imparted the knowledge that this is not your grandfather's filter. This is a very innovative process. It uses very simple techniques. In some cases, or I should say, as far as the vessel is concerned, a conventional vessel, but the process control is very advanced, very novel, and it's been very effective over the last 10 years for Blue Water in treating water for a lot of our industrial clients. So this is in contrast to chemical precipitation processes. We use these upstream. Again, these are not for polishing and trace metals compliance. These are for precipitation of high TDS, and these are again very conventional treatment technologies for kind of as a roughing technology where you're removing high levels of metals, high TDS, etc., as a prep to go into the Blue Pro process for your compliance stage. Coagulation followed by filtration. Again, Blue Pro is not this. Coagulation followed by filtration, that'd be other sand filters in the market that may look very similar, like a Dynasand or a Super Sand. But again, they don't have the same process within them. They don't use adsorption, they use coagulation filtration, which, as I highlighted before, you're forming up large particles and you're actually plugging your media, which is unsustainable. It's really a process headache. So it's different than coagulation filtration. You'll also see the coagulation filtration method in rotating in cloth disc filters, fuzzy filters, etc. And again, there's just a lot of reliability concerns, a lot of sustainability concerns with that method of treatment when you're using a filter. So again, adsorption is really the key to an effective process for compliance. Membranes, a lot of people will use membranes for these low levels of compliance. Arsenic is a pretty popular application for membranes. But when you're using the membrane, an ultramembrane, they kind of glass over pretty quickly with metal precipitates, especially when you're specifically trying to remove metal with them. So it's another sustainability issue. And really the theory or the methodology of process for membranes is the same as coagulation filtration. You're adding chemistry up front, and you're trying to form a larger particle that physically will not fit through the membrane openings. And so, again, it's a sustainability problem, a very costly sustainability problem, because membranes are not cheap, and they're not cheap to replace. So, again, the Blue Pro process overcomes a lot of these challenges in process. It leads to a much lower cost of ownership, lower O&M cost, lower replacement cost for equipment to keep that process running and your plant online, because really we don't want to worry too much about water. We're in the business of making energy and keeping those customers happy. So I want to thank you for joining me. I'm now going to open up for questions. If you have any questions, please use the GoToMeeting interface to type in your questions. There's a chat and questions box where you can type in any process questions that you might have, and we can address those over the next 5 to 10 minutes. I allotted 1 hour for this, and we're about 5 minutes to the hour, so I'll take questions for a few minutes here. I do have a question here that came in. Have you had any FGD applications? And the answer is yes. We have a couple of FGD applications. Most of our work today in FGD has been on the bench scale and on the pilot scale. We do not have an installation yet in an FGD application. Although that might not be completely accurate, because I'm not sure what the what kind of energy plant our team was recently on in Iowa. But I do know that we have quite a bit of history with FGD on bench scale and on pilot scale. Another question that came in is Blue Pro effective for selenite and selenate? So that's another very common question. And selenium and arsenic are kind of different animals regarding removal absorption technologies, any kind of removal technology really, because they each have a specific oxidation state that has a fair efficiency at absorption and chemical uptake, and then they have an oxidation state that does not. And so for selenium, I believe it is the selenite form that is a little bit easier to treat, but the selenate is more difficult. And I believe that is correct. It's the reduced forms for selenium. I do know for sure that when you're dealing with arsenic, it's the oxidized form that you want. So it'd be the arsenate. And the reason is they just have much better, much stronger absorption properties. Their absorption isotherms are closer to neutral, and so the process parameters are much easier. So there can be some challenges with those elements if they're not in the proper oxidation state, but there are ways to overcome that with either adding an oxidation process or by reducing with some form of an acid process. There's another question about nitrate and nitrite. So nitrate and nitrite are very simple to remove with a biological process. They're not very cost effective to remove with a purely chemical or physical process, but our biological reactors, and again it can be the same treatment stage, are very effective at nitrate removal. We have many installations across the U.S., across the world, for biological denitrification, and within the industry. We've done very similar to the gold application, which I'm going to page back to real quick. where you have a very high level of both nitrates and nitrite coming from an industrial process. And again, this is a gold mine. Upstream is actually the removal of cyanide. So they have a cyanide process upstream of this. But the end result is they have a lot of nitrates to deal with. And again, very effective for dealing with those nitrates. Most of the time in the FGD applications that I've seen, if we're still on that thread, most of the time I noticed that the nitrates are much lower than this application. I would say more in the range from 30 to 70 milligrams per liter. And the lower they are, the less detention time you need for complete conversion. Another question that I have is unit cost for treatment, and a lot of people are looking for that cost in a capital cost per gallon per day treated, a O&M cost per gallon per day treated, and it's really going to vary from application to application. Most of the treatment plants that are 1 MGD to 3 MGD, they're from an equipment cost only standpoint, they're going to be well under $1 million. And then as far as a chemical cost scenario, it all depends on what specific elements are being removed. And I should also backtrack a little bit and say, hey, if that's a single-stage system versus a two-stage system for varying elements, those capital costs might need to be adjusted a little bit. But the O&M costs are typically very low because for that filter system, that footprint, everything, the energy input is typically between 10 and 20 horse max. So it's a very low energy input, and then the chemical input is whatever the process needs, and that typically is a fraction of the capital install cost, which most people like to hear because I've seen so many clients that are literally spending millions of dollars in chemical every year for compliance. So it's going to vary for every application. But the bottom line is, with specific process parameters for your applications, we can do a life cycle cost analysis, certainly even at the bench scale. One of the questions that I have here is application in I'm trying to decipher here for a minute, sorry. One of the questions that I have is in regard to other process chemistry, what's typically used for targeting a pH adsorption isotherm. And typically what we're talking about there is just a straight up pH chemical. So we're talking about acids and bases, whatever's commodity and inexpensive, and whatever will not interfere with other parts of the permit. So for example, some people have sulfates on their permit, and because of the sulfates, the higher levels of sulfates, you want to stay away from stuff like sulfuric acid. HCl in that situation would be a good process choice. If you're trying to remove transition elements like zinc and you have to actually raise the pH, we're looking at caustic, mag hydroxide, limes, soda ash, etc. Those are pretty commodity and inexpensive chemicals. And then if we need a polymer chemistry, there's a lot of polymer chemistries that work very well that are very inexpensive, upstream in a clarification stage before we get to adsorption. So one of the questions that came up, does Blue Pro pass a TCLP? And it's going to, again, depend on your target parameters. So it'll pass the TCLP for a variety of applications. It just depends on what's in your water in the first place and what we're targeting for removal. So in my experience, given the periodic table that I had shared earlier, and I'm going to pop back to that real quick, we can remove a variety of different contaminants, but again, we need to know what's in your water to begin with, and that's where we like to do, bench scale analysis. That's the most economic upfront analysis for a new project, where we can say, hey, this is what's in the water, this is what the process will remove, and this system is very capable. Again, from just a water quality standpoint, it will produce water quality that's near to reuse standards as far as solids, dissolved solids, and absorption of these trace elements is very highly efficient. So I think for that question, I'd like to see specific process parameters, data, application targets, etc. We are out of time now. I wish we had a little bit more, but if you have any further questions, I'm going to pop to the end of my presentation again so that those email addresses are on the screen. So any further questions, you can just email sales@bluewater-technologies.com. Any of those process questions can be answered. We will basically put you in touch with a regional business manager and an apps engineer, and they can definitely answer your process questions. If you're looking for PDHs, email mcphee@bluewater-technologies.com, and we can get you PDH certificates for your attendance. So I want to thank you all for joining me on this webinar. I hope that I have given all of our guests a broad overview of the challenges that dischargers face today in our economy. I wish to thank you for the opportunity to summarize some of our equipment solutions, and I look forward to discussing your particular challenges in more detail going forward. So again, thank you and have a good day.